Hello everyone. So during the last session, last lecture, we looked into the how to code, the important points regarding RT coding in Verilog, using Verilog. Now in this section, we will now look at how now you have assuming you have the RTL files prepared. I'll now go into how to read this design into design compiler, what to look out for. So if you look at the steps here, so what we discussed in the last section was about this developing HDL file. We've already seen how to specify libraries, what is inside the library. We saw, we learned about different variables, base library, target library, and all that. Now we will be looking into this. In design, we will be looking at the C commands, analyze the libraries and these files. And during the whole unit of synthesis, I'll keep following this flowchart. Now let's look at assuming you have RTL files ready with you, what you could do with them. So the first important command is analyze. It translates HDL into intermediate format. Let's not worry about what that intermediate format is. It's something internal to design compiler. This command is recommended for reading RTL. This is very important. When you want to read RTL, when you want to read Verilog, this is the command you should use first up. So any command you can get help in design compiler by using this. So analyze minus help will tell you what options are available. If you do a man analyze, MAN space analyze, it will give much more detail about each and every option. So I would recommend, like wherever it's the first time you're using any command, I would recommend using these two options. So analyze minus help will give you a quick summary of what all options are there, and man analyze will tell you in detail what it is a lot more detailed than the minus help option. So its options are minus library name, minus work library name. So these two are just to specify what library you would use to store the intermediate output of the after reading the RTL. This is in conjunction with defined design list, is what we saw earlier. These are anyway you could a parenthesis here. A parenthesis here means that this is an optional argument. So minus library name, minus work library name, they are both optional arguments. Since this command is common for Verilog and VHDL, that's why you have two arguments, minus library and minus work. So but once you start coding in Verilog, most probably you will not need these two options. If you define the design list correctly, you will only need this one, minus format string. This will tell design compiler what format it is. So for reading a Verilog, you would say analyze minus format Verilog. Again, you can read about these options, minus update, minus schedule, create, update, and all that, because these are not used frequently. These are used for some advanced cases, some very special cases. You could read about them. Then this is a very special case. Minus define macro name. So you go back to Verilog. You can have parameters. You can have macros defined. Obviously, this is only for Verilog, applicable only for Verilog. And so Verilog has if-def macros. So many times RTL code will have if-def statements. So you could define those macros. So let's say I want to set the constant. I say that let's say I have an option in my design to set a particular register to either 0 or 1 based on two use cases. So I can define a macro. I can say if def, let's say if def 0, then I'll assign register to 0. Otherwise, I'll assign that register to 1. So by defining this, if you do not define anything, it will go to the else part. So it will define it. It will specify the register. It will assign constant point to the register. Using this minus define macro, you could say minus define 0, and correspondingly design compiler will parse that, and it will assign the register value to the 0. This is very similar to the preprocessor directive of C. So once so analyze, what analyze actually does is it enables you to define macros while reading a Verilog or VHDL file. Obviously, for VHDL, the macros are not supported there. So it analyzes simply, and it will also tell what all syntax error to your RTL files contain. So once you pass analyze, it means that at least your code is syntactically correct. Then what follows is second command is elaborate. It is the second step of SDL translation. Elaborate will actually build the GTEC database. So after you have read in the file using analyze, elaborate will map. It will start the mapping or rather translation of your code into GTEC. It will start mapping it into GTEC. What it does is that SDL parameters are expanded. So you have a parameter command in Verilog. All parameters will be expanded. It will infer register and latches. We saw in last lecture how does design compiler infer register and infer latches. It will actually infer that, and it will link the design. What linking design means that if you have a PLL or a memory, and that memory is part of your should be a part of your link library, it will now map. It will now link the design. Elaboration means the design should be completely linked. Each and every component should be mapped. If it is not able to link the design, it will error out. So it supports parameter passing and architecture selection. Architecture selection is VHDL specific. Parameter passing is Verilog specific. It is so analyze, elaborate. Both these commands combined together are recommended for reading RTL into design compiler. Again, you could do elaborate minus L. Again, it has so many options. This is VHDL specific. This is Verilog specific. Again, there are you could read about the options here. Most important thing is design name. We'll see a bit more about gate block later in the flow. The design name is the top level of the design. Now, in the last lecture, we saw in the design of an accumulator. The accumulator contains an adder, a mux, and a register block. So the top level module, which is the accumulator module, will be given here now because that's the top level module. So you only give, so you analyze all the RTL files, but elaborate only from the top. So you should be very clear about this concept that elaboration should be done on the level at which you want to perform the synthesis. So elaboration, the design name here will be the module name of the top level job. Once you start working yourself in design compiler, or once you see few examples, we have example videos later on. It will be very clear. It's perfectly very clear. Now there's one more command called read file. Now read file is used on RTL. Read file performs analysis and elaboration in one step. So this is exclusive. This command is exclusive. This should not be used along with either you use analyze, elaborate, or you use read file for a particular design. You only use one, either analyze, elaborate, or read file. But read file does not perform any parameter passing or architecture. It has limited functionality when compared to analyze, elaborate. It is recommended for reading map netlist. Why do you want to read map netlist? Now let's say you are doing a big design and a part of the design is in the netlist form. It is a very common occurrence that a block which let's say you are procuring from outside, from some other team or from some other company, they might give that block to you in a netlist format. They do not want you to see their code. The code is proprietary, confidential. So they will give you the netlist. They will give you the gate netlist. So how do you read the gate netlist? You use using read file. So you read file, you specify if it's Verilog or DDP or DB and so on. Again, you could read about all these options in design compiler in detail. However, you can use this to read the RTL also. If your RTL is simple enough, it does not have, it supports macro name reading. If your RTL does not have parameterized design, you can go and read about parameterized designs in Verilog. If your design does not have parameterized design, then you could actually use this read file for reading RTL also. Or let's say all your code is, you are just compiling one module. You are just synthesizing and testing only one module. So you could use read files. There's no need to do a separate analyze and analysis. Now let's look at one of the most popular GTEC sequential cell. It is called SEQGEN or SEQGEN. So whenever SGL compiler reads the design, it uses this SEQGEN module to represent an inferred flip-flop or a latch. So whenever it encounters an always block and sees and deduces that it's either a latch or a flip-flop, it will map that logic onto a GTEC sequential element. Please note that this is a GTEC element. It is not a technology. It is not a standard cell library cell. It's a generic cell. As you can see that this generic cell contains clock, data in, clear and enable are asynchronous pins. Enable is asynchronous set. This is asynchronous reset. Next state, reset. These are synchronous pins, synchronous toggle, synchronous reset. So as you can see by the pin names itself, this block can actually represent either a flip-flop or a latch or a toggle flip-flop, a number of sequential elements just by some tweaking of the you could set some constants and you can represent any sequential block using a SEQGEN. Let's take a flip-flop example. So this is the code of a D flip-flop with asynchronous reset. How do I know it's an asynchronous reset? Because reset is a sensitive tool, as we discussed in the last lecture. Now, design compiler, as soon as it reads this code, as soon as it elaborates, please note, elaborate is the command that will force a GTEC mapping. So as soon as it elaborates, it will map. Now Q is now it analyzes and sees that Q is the output of the flop. D flip flop with asynchronous reset. So now it will connect Q. It will instantiate a SEQGEN. It will connect the Q here. It will connect the clock. Here is asynchronous reset. Data goes to next state. So next state is apparently data. Okay. And rest all synchronous, asynchronous, clear and set, asynchronous set. They are all set to 0. Synchronous enable is set to 1 to enable the function of this SEQGEN. So usually, in most of the cases, you do not need to be concerned about the functionality of SEQGEN because it's ultimately an intermediate step. What you are concerned about, first thing, is I'll go into this. You should look at the elaboration report. And second, please note, till this step, synthesis hasn't been done. We are still reading the design. So once the design is read, once it infers flip-flops and latches, the design compiler will simply map flip-flops and latches to a SEQGEN. There are a many number of GTEC cells also. So there are GTEC OR, GTEC AND, GTEC NAND. So it will map all that. So the first step in synthesis, if we go back and try to remember, is translation and mapping. So translation means reading of the RTL. Mapping means mapping the RTL into GTEC. So this is one example where it will map the sequential logic into SEQGEN. Now let's look at very important thing, very important sort of report, which is called inference report. Let's first look at the inference reports for registers. Now SGL compiler provides inference reports that will describe each inferred flip-flop or latch. So each of the always block, sequential block, will get mapped to design compiler at the time of elaboration. When you say elaborate, the top level design, it will start throwing out reports. the enabling or disabling of generation of inference reports can be switched on and off by using the SDN in reporting level variable. So the SDN in prefix here represents that this SDN in variable or SDN in variables are used by the SDL compiler part of the design compiler. So SDL compiler is actually the engine that reads in the Verilog. So SDL in reporting level variable controls the enabling or disabling of these elaboration reports. By default, if these are enabled, these reports are very useful during the analysis of the design. So what do? You read in the RTL, and wherever you expected a latch or a flip flop, you look at this report. So it will say, for example, for this, as soon as it reads this module, it knows Q is a sequential element. So it will add a suffix here, Q underscore. So it will add underscore reg to the name to show that it's a register. So it will say register name is QS. It will tell that the type is flip flop. If it detected a latch, if it inferred a latch, the label here would be latch. It tells what is the bit. It's 1 in this case. It tells whether it's bus. So bit is 1. It's not a bus. MB tells it's multi-bit. Let's leave it for now. We don't need to be concerned about this for now. These are very important. AR, AS, SR, SS. These tell you that whether it has inferred an asynchronous reset, asynchronous set, synchronous reset, or synchronous set. Now this inference report is not consistent with the code here. So now this code here tells it's an asynchronous reset. So there should be a So asynchronous reset is a yes. 1. Multi-bit is no. AR is yes. That means Synopsys design compiler has correctly identified that you intended to have an asynchronous reset here. So for every register during the start of your coding process, when you start synthesis, first synthesis, you should carefully look at all the complete inference report for each and every register. What about the combination logic? If, let's say, for example, your combination logic is not correct, and we saw a few mistakes in the previous lecture where few small mistakes could mean inference of a latch. So if you see a latch here and you did not mean it, then you can see, then you can search for latch in this report. You can grep for the latch in this report, elaboration report, and correct all such cases which are unintended. Usually, the most common mistake is not specifying every case in the case analysis statement. It results in a latch. You could grep for latch in this report, elaboration report, and correct on it. Now let's see how does an effective coding get rid of the unwanted registers. So sequential elements are not easily optimized on. It's not like combination logic. Sequential elements represent timing sequence, and design compiler in most of the cases, when it sees a sequential element from your orders block in your RTL code, it will map them to flip flops, and those flip flops, it doesn't know if they should be optimized off or not, right? They represent a timing sequence, and they represent the way you code the RTL. So you have to make sure that your RTL should contain sequential element only when it's desired. It's the duty of the designer to make sure that. If you have unwanted sequential elements, obviously your area will be more. Let's look at this case. This count, you have always at POSIX clock. You have a reset. So now this is question: is this a synchronous reset or an asynchronous reset? Answer: it's a synchronous reset. Why? Reset is not part of the sensitivity list. It's a synchronous reset. Count goes to 0 if it's reset state. If it doesn't get reset, count increments. There are 3 outputs here: AND bits, OR bits, XOR bits. AND, OR, and XOR all get these values. AND gets AND of all bits, OR gets OR of all bits, XOR gets XOR of the count. Now, when it reads the code in this particular always block that starts here and ends here, it sees following registers. It sees count, it sees and, it sees or, it sees dot. Now you see correspondingly, you see the inference report like this. OR bits, so it will append underscore edge, OR bits edge, count edge, XOR bits, and bits edge. All it is deducted, they are flip flops, it's a POSIX block. It specified the width here. One of them, that is count edge, is a bus. It did not, although you expected that reset would be a synchronous reset, it did not. It does not have a Y for the synchronous reset. It does not have a Y here, so it is not deducing that. It is not inferring that this has a synchronous reset. I'll tell you how to correct this. How to make sure that you tell design compiler that it's a synchronous reset, because it will affect the way implementation is done. It will affect the way the netlist is generated. Let's leave it. Let's hold that thought for now. We'll see the written lecture itself how to encounter that. But important thing is that, do you actually want AND bits, OR bits, and XOR bits to be registered to this flip-flop? So you should carefully look at this code and decide. But just taking a first look and just delving it a bit deeper into this, we can say that AND bits, OR bits, and XOR bits are combinational operations on the count, and most probably it is not needed that they be represented by flip-flops. How do we correct this code? Like this. Again, we go back to the basics. First thing, we have to separate combinational sequencing. So here is how we do that. We separated the sequential part, and the combination part is another always block. Now, when it sees this always block, design compiler will assume, obviously it will know that these are combination outputs. It will infer only count rows as register, not AND bits, OR bits, and XOR. So this is the way we have to be very, very clear while coding what is sequential, what is combinational, and code according to that. First, very important and basic rule: separate the always blocks for combination and sequence. This is very, very important. This will make sure that you are not having number of flip-flops are not more than what they should be. This is a particular case of unloaded registers. So SGL compiler will not automatically keep unloaded registers or undriven flip-flops or latches in the design. These at the start itself, SGL compiler knows these are not necessary, and they are removed even before the design is completely optimized. So they are removed in the first pass of optimization. What are unloaded registers? What are undriven flip-flops? Let's give an example. So a module fuel, you have 3 inputs of 2 bits each: IN1, IN2, IN3. You have input clock, output out. You have 2 registers, sum1 and sum2. You have wire save. Always at POSIX clock, sequential element. There is no reset here. Sum1 gets IN1 plus IN2. Sum2 gets IN1 plus IN2 plus IN3. But now the output here, the out, there is only one output. Out gets the sum1's complement. Save gets sum1 plus sum2. But is save an output? Is save feeding to any output? No. There is only one output out, and out gets sum1. What about sum2? Sum2 is in no way affecting any output. Although you have a wire, but this wire doesn't go anywhere. You assign save to something, but this save is not going to the module boundary. So now SGL compiler knows, DC knows that save is not used, and sum2 that is used to generate save is also not used. Although sum2 is registered as a flip-flop, it's a valid flip-flop, but the output of this flip-flop goes to a wire, and that wire is hanging. That wire is not connecting to anything. So the combination logic of save is not saved, and the register, this flip-flop sum2 is not saved. Both of these are optimized off. So what you get is registers corresponding to someone. That's it. Again, you have to be very careful while coding that if you are not using sum2, don't even put it there, it will increase confusion. Otherwise, if you intended to use sum2, then you should make sure that these registers go to some output or drive something. Otherwise, they will be optimized. However, in the initial design phase, let's say I coded this. I intended to use sum2, but for a later period. So, and you still want to see what is the area impact. You want to analyze what is the area impact, but you do not know where sum2 will go for now. You can tell DC to keep the unloaded registers. So here is one more example. Here is one more variable called SDL in preserve sequential that tells DC which cells to preserve. So to preserve unloaded undriven flip flops and latches in your VTech necklace, we set SDL in preserve sequential to all. To preserve only flip flops, if you set this to all, DC will preserve everything, all the registers, all and latches. If you set this to FF, it will preserve only flip flop. If you set this to latch, it will preserve only latch. To preserve all unloaded sequential cells, including unloaded sequential cells that are used only as loop variables. Please ignore this for now. We don't need to go deep into this now. The loop variables are part of forage. So for loop, the loop variables, and a loop variable in a software concept, a loop variable is nothing but the loop variable counts. But in case of synthesis, in case of hardware, a loop variable simply means that the hardware will be either repeated depending on the kind of logic you write, or there will be some counter. So it is not necessary that the loop variable will itself be a clock. For example, if the hardware is repeated, let's say you have a loop of 5, and it means that corresponding hardware should be repeated 5 times, there will not be any flip flop that will represent the count of 5. So if you set this variable to all plus loop, it will start saving the loop variables also. Please, you should be very careful in using this variable, because by default this variable is not set. It's set to the default value, means that it will not keep unloaded registers. If you choose to enable it to all or FF to latch, you should be prepared to see an area increase. So you should be very careful while using this variable. Now, so we saw register inference, we saw a few inference reports. Inference report is of this type, register name, type, and so on. But there are some limitations on register inference. That means I've already stressed the fact that Verilog, complete Verilog is not synthesizable, only a subset is. So you should be careful while writing RTL for synthesis, and these are the limitations that tell us that in what all cases SDL compiler will have problems in inferring a flip flop or a latch. So whenever we model asynchronous behavior using if block, the tool does not support more than one independent if block when asynchronous behavior is modeled. If the always block is purely synchronous, multiple independent if block are supported. We'll see few examples of this later. It cannot infer flip flops and latches with pre-state outputs. It assumes a flip flop and a latch. It assumes will always have two states, either 0 or 1, not Z. If you have a special library cell that has this case, you should instantiate it. It will never infer. Even if you have a flip flop with Z output in your standard cell library, it will never use it. You should, if you assign the value to be Z in your always block, it will error. It will error out. It cannot infer flip flops with bidirection pins. The flip flop pins should be either input or output, not an out. Again, whatever special case, whatever cases are written here, if it is not supported and you have a cell that implements that, you should instantiate it specifically. You cannot infer flip-flops with multiple clock input. Again, you should have flip-flop with only one clock. That means you're always at the rate POSIX. Sensitivity should have only one clock. You cannot infer multi-port latches. Again, it does not infer register banks, register files, and nothing but small memory. So it will not infer. Let's say you have a small memory as part. You unknowingly you specified a register file as part of a target library. Design compiler will never infer that. Inferring means it will never automatically pick up some hardware to replace your RTL. Inferring means that. How do you encounter this? You do not code the RTL part basically, you instantiate that part. So for example, you have a register file, you want to use it, you instantiate the register file. You do not rely on design compiler to infer that file. So although we can instantiate flip-flop with bidirectional pin, design compiler will ignore that. If we treat them as black box, that means it doesn't know the functionality. So if you use an if statement to infer deep flip-flop, this is very, very important. The if statement must occur at the top level of the always block, like this. If you have some statement here and you want DC to infer this as a asynchronous reset flip-flop, it will not do it because the first statement is never a statement. So very important coding guidelines. Whenever you want to write the code for an asynchronous set or reset flip-flop, first line should be always if reset or if set. Else part you write your rest of the code. But first line should always tell DC what is the reset functionality. You should be very, very clear about it. So this tells you that you cannot arbitrarily code RTL. You have a sort of a set of guidelines which you should follow to make sure that design compiler does the correct inference, draws the correct inference. We talk about finite state machines. Again, there are a set of rules about finite state machines. The set of rules, it must never be assigned a value other than defined state values, but finite state machine cannot have latches. It must always have flip-flops. The FSM register, all these are register rules. Must never be a module port, function port, or task port. The state register, that is, we are specifically talking about the register that maintains the state. It cannot be a port of any module or function or task. It can only use the operands like equal to or not equal to, that is the comparisons, and not any other expressions. Since states will always be compared, only compared, there won't be any data operation done on it. There can be only one FSM design per module. If you want to have multiple FSMs, you need to have separate modules. All ports of initial design. So again, bidirectional supports and outputs are not supported here. Combination feedback loops are not supported. Although combination logic that does not depend on state vector is accurately represented. FSM will should have only one clock, and optional synchronous or asynchronous reset signal. This is again a variable which tells a DC whether or not to automatically infer FSM. Let's look at one example here. So you have 4 states: set 0, hold 0, set 1, hold 1. So states are represented by parameters. It's a very good way of coding in FSM. So this is a one hot coding. That means that only one bit will be 1 at a time, and so 4 states are represented like this. Set 0 will have LSB 1, hold 0 will have bit 1 1, set 1 will have bit 2 1, hold 1 will have the MSB 1. So 4 states for one hot encoding you need 4 bits. So you by using parameters you define all these states. Current state is current state is nothing but the state register. So the first always block is the sequential block. This is the sequential block, which tells DC that this part here is the state register. Very simple way. This is a synchronous. This is an asynchronous reset. Current state gets next state if it's not reset. And then in a separate combinational block which forms the combinational part of the FSM, you write the operations that will take place based on the state, based on the current state. So current state you write you use a case statement. So current state, if it's something is if it's set 0, based on this you follow this diagram and you start coding. If you have an input dependency, you write it here like this, if and else, and so on, and make sure that all the cases are covered, all the states are covered. Now in this case, if you set the variable, this variable FSM model is running to true, design compiler will give this kind of statistic. This statistic is not matching with the code here, I know, but you could have. It will tell you what the states are. It will give you the parametric codes here. It will tell you how many number of states are there. So you can match this inference report with your code and make sure that the design compiler understands what you wanted it to understand. And please also see that this FSM follows each and every rule written. Just try to map it one to one. You can use this code as help to code whatever FSM you want. So first you should have a state diagram, and then you can code like this. Now let's look at a very important concept of SDL compiler synthesis directive. So SDL, what is a synthesis directive? These are special comments that will affect the action of SDL compiler and design compiler. These comments are ignored by any other tool, so they look like comments, but they are special comments. They begin with // synopsis or // synopsis. There's one more notation, but we will use this // synopsis notation in all our examples. So they carry special value for design compiler. It will change, it will modify the way DC reads those statements. It will help you in some cases. These are dangerous in other cases. It will, SDL compiler will report a syntax error if you use // synopsis on a regular command. We'll see. Now let's look at the few most famous synthesis directives, when to use them, when to avoid them, and so on. Async set reset. Now we saw that there's a rule that if we want to code asynchronous reset or synchronous reset, whatever, the first statement should be if. It is very important. Now in most of the cases, the tool will, so as I mentioned before, asynchronous set or reset will only be implemented only if you have a corresponding standard cell in your library, corresponding block or latch with asynchronous reset and reset in library. Only then you could map it. So in most of the cases, if you have an asynchronous set and reset and you have correct coding done, then you do not need to use this variable. But in some cases, if you see that, even if you write the correct code, I'm not sure what that case might be, but if you see that this is again an old variable, I have not seen people using it a lot. So you should try first not to use it. See the inference report whether DC has correctly inferred your asynchronous set or reset. If it doesn't work, then you can try it out. You can write the comment like this: // synopsis asynchronous set reset, and you tell DC that this reset is the one I am talking about. This reset is used here always under reset. It is used in the if statement, and you tell DC that this is the asynchronous signal. Use this only on single bit signal. Now SDL compiler will see it, and then it will check whether on reset have you assigned any constant to the register. If you have done it, it will try to look in standard cell library if you indeed have an asynchronous reset or a set block, and then it will map. Thus, we have asynchronous sync set reset. Now this is important. This is used to infer a D flip-flop with a synchronous set reset. When we compile a design, The setgen inferred by SGL compiler will be mapped to a flip-flop in the logic library with synchronous set reset pin. Or if your library does not contain a flip-flop with a synchronous set reset, then design compiler will use the regular D flop and build the synchronous set reset logic in front of the D pin. The choice depends on what method will provide a better optimization result. It is important to use this directive to label because it tells DC that signal should be kept as close to register as possible during the. Now, first assume that you have a flop in your standard cell library that has synchronous reset and reset, and you want to use it. Then you simply tell DC that okay, by using sync set reset, that yes, I want to use this flop, and this is my particular reset pin. Reset signal, DC will directly use it. This is the best case scenario. If you do not have a corresponding flop in the design, now DC cannot map it, so it will build a combination logic. Now this directive tells DC that my reset pin is very important. It should be kept as close to register as possible. Otherwise, what may happen that this reset pin will be a lower priority signal. It will go. There might be a number of stages between this reset signal and your flop, and correspondingly, you might face problems in data implementation. This is not an easy example to tell right now. At the level when you are starting to learn synthesis, but as you go on, you will find that this is a problem in bit design, where you have complex synchronous sequence. So, if your synchronous reset is being generated by some complex logic, then and you want to keep that reset close to the flip-flop, then you use this. Let's see one example. Here again, inference report is the way to go here. You read in the design, you elaborate, and you look at the inference report. If it tells that asynchronous set is yes, your job is done. So first, my recommendation: do not use this. Follow proper guidelines. That is, first line should be if set or reset. If you see that your corresponding option is set to Y, your job is done. If you still see N here, you can use this. Use the statement synopsis sync set reset. Here the signal is set. If set, use set to 1, and verify with respect to the inference report. If the inference report is correct, you can go ahead. One more infer mux. Many times we have a lot of case statements, and we want the tool to implement this using a mux, not the combination logic, not add-on cell, not other kind of combination logic. This might increase the area or decrease the performance, but many times you would want that for. There are many reasons why you would want that. Let's say your functionality is not final, and you know that you might need to change something in the netlist later. Then a mux kind of structure, a mux tree kind of structure is easier to understand in the netlist as opposed to an add-on structure. A mux kind of structure, mux tree kind of structure has many times it has better timing but more area. So if you want a design compiler, you want to make sure that it uses multiplexing logic it picks up the mux logic in your RTL to multiplexers in your logic library. You need to use. The first step is you can use a synopsis infer mux here. Then you can see your GTech whether so corresponding to setgen sequential block, you have a mux of block here. It looks like this. You have select signals, you have data signals, you have output. So if you must use simple variables as control expressions. For example, if we use not input A but the negation of input A, it will not infer a mux of. So whenever it infers a mux of, you use infer mux. When it infers a mux of, you can be rest assured that it will use the mux kind of structure from standard cell library to implement a mux tree in most of the cases, unless and until the timing or area is very bad. So as you start coding, I will not recommend you to use this always. From the last three, we saw 3 directives. We saw async set reset. I will not recommend that you use this. If you do proper coding and your library has the corresponding cell, you are good. You can use sync set reset for complex synchronous set resets. So these are very special cases again. Again, the first thing you code without using these directives. Look at the inference reports. See that whatever you expected is there. If not, then you can actually study about these directives and start using them. So that's why I am mentioning only the famous ones. Again, with Infernux, I would not recommend it to use it unless it's very much necessary. Now comes the full case. So the 2 things here, full case and parallel case, are the most popular and most misused compiler directives. You should be very, very careful. First thing, you should not use it. But why are we studying this? We are studying this because in case we get an RTL code and somebody has used it, we should know what it means. We should know what kind of dangers it gives us, and we should know how to solve those problems. So full case prevents SDL compiler from generating logic to test any value that is not covered by the case branches and create an implicit default branch. Now let's say you have a set of case block and all the cases are not mentioned here and there is no default. What does that mean? It means that DC will assume that in the cases that you have not specified, you want to preserve the value of the output and correspondingly it will infer a latch. You obviously do not know this. So what is the way out? The first way out is to correct your code. Use a default statement. Make sure that all your case analysis, all your case is complete. You mention all the cases, but many times it's not possible. Many times the designers will assume that or will know that the input case we want to code will never come, so it doesn't code it. So then to prevent a latch, you can use this. You can say synopsis full case in front of the case statement, and DC will now not infer a latch. We will see 2 examples. Parallel case will tell DC if you do not use a parallel case and you have such a condition that more than one case can be true, then it will make a priority kind of encoding. It will make a priority logic. DC will make priority logic to make sure that this prevents SDL compiler from building additional logic to ensure that first occurrence of a true branch. So there are more than one branches that are evaluating to true, and it will make sure that the first occurrence of the true branch is executed if more than one branch or true at a time. This will create extra logic. This will create extra priority logic. So you want to prevent that. So that is why you tell DC that, okay boss, all these cases are exclusive. That means at one point only one of them is true. So please do not add any extra logic, any extra priority logic. So DC will not do that. Now let's see the inference report. DC will tell you at corresponding to each case branch, each case in your design, each case statement in your design, DC will produce an inference report similar to the system, similar to flip-flops. For example, 367 line number, it will tell by line number and file number. It tells me here that line 367 of some file has a case statement and it is automatically full and automatically parallel. That means that we haven't specified any compiler directive, we haven't specified full case, parallel case, but by design itself, this case block has all the cases covered and only one case is true at one time. This is by design. So it tells auto and auto, it is automatic. This is the best case scenario. What if you forgot to code a case? Now here it is telling me that at line 108 the case block is not full. That means all the cases are not covered, but it is current. For the other case, it will tell that okay, boss, it is full. So if it is not even full and not even parallel, it will say no and no. The first two cases here tell us that compiler directives are not used. Now I started using compiler directives. So this tells me that at line 59, the case block, it is full, yes, it is full, but you have used a parallel case directive. User means that you are telling DC as a user that treat this as parallel case. If you write full case, it will say user/user. Now this table tells us that what happens when the case analysis description is full and parallel, no additional logic is generated. So you should achieve for this. For your case blocks, if you do not want priority logic, if you do not want latch, you should achieve for the first case. By design, your code should be full and parallel code. If it is full but not parallel, then priority encoded logic will be there. It will generate logic to ensure that branch listed first takes effect. If it is parallel but not full, latches are created. If it is neither parallel nor full, then it will generate priority encoded logic and it will also create latches. Please understand this table very carefully. Spend some time over it. Try to code cases and see where you might miss and it doesn't become a full or doesn't become a parallel, so on. Let's see some examples. Here, so this is the case statement. The select is of 2 bit. The maximum it can have 4. So all 4 cases are coded here. So this is by default full and obviously by default parallel. Why? Because only one of them, this can be true at one time. Cell can either be 0, 0, 0, 1, 1, 0, 1, 1 at one time. All the cases are specified and only one can happen at one time. So it is parallel and full both. You do not need any compiler directive. Second case. Select is 2 bit. You can have 4 cases here, but only 2 are coded. So it is unknown what happens when cell equals 0, 1 and 1, 0. In this case, SGS compiler will generate logic to test for any value that is not covered and create an implicit default branch. Keyword is implicit. It will assume a default branch and it will try to make sure that Y here remains unchanged. That is why it will use latches. What you can do to correct this case? Use a default branch. Use a default branch, or now you know that in some cases the designer knows that okay, cell cannot take value of 0, 1 and 1, 0 ever. Now select is an input here. What if designer knows that select will never take 0, 1, 1, 0 and he is a bit lazy, he doesn't write default here but writes a full case here. He cannot do that. Now by telling Synopsys DC that okay, I have written full case here, it will assume it's full and it will not infer latches. This is the case here. So here we see that Synopsys full case is used here for the first case. Case is IN is 2 bit. Again, only 3 are written. There can be maximum 4 cases. Default is not there. In the first case statement, condition IN is equal to 3 is not covered. However, designer knows that IN3 will never occur and therefore sets a full case here. So, no latches. Both parallel case and full case are used here, which is again kind of a one-hot encoding. Designer knows that, so current state is a 4-bit signal. It has 16 states, only 4 states are coded here. So only 4 states are coded here and this is one-hot coding. So designer knows here that only one bit will be one at a time, and all other cases are invalid. They will not even come. This is a statement like that. So he, instead of writing all the 16 cases here, he writes what are the valid cases and tells DC that it is full and final code. That means DC will not have any priority encoding. It will not have any latches. So this is, you will see in my experience, I have seen a lot of RTL like this. Because in this case, the designer he knows very well that these cases are invalid, they will never occur, and so his simulation test cases also don't have these cases, so he never faces a problem of simulation synthesis mismatch. But again, the important thing is that designer should know what he's doing. If you're not confident, if there is even a 1% chance that these cases can occur, then please make sure that by design your case block should be full and parallel, and there should not be any need to use the full case and parallel. So a word of caution, a final word of caution. Although the full case directive and although both full case and default clauses prevent latch inference, they have different meanings. The full case directive asserts that all input values have been specified in no default clauses necessary. This is for the case where you do not have default and you are using full case. You are telling DC that assume that all are covered. But the default clause explicitly specifies the output for any undefined input value. Now what is the difference here? In terms of the hardware generated. In terms of hardware generated, in the first case, let's say we take a case here. Now here, let's say I write default out is equal to B. So now in this case, let's say there is some hardware generated. Compare it with the case where default is not specified. Now if default is not specified, if not a full case is given, DC will assume the value of output. Such a value of output, will assume some value, either 0 or 1 or 2 or 3, whatever, such that the area is minimal. So it's like the Carter map optimization. But let's say you specify default here and fix the value of output. It might increase the area a bit. Why? Because now the value is not don't care, it is some other value. So the optimization in case of don't care is better when compared to a non-don't care case, as you all know from digital design. So this is the difference here. Now what can we do? We do not want to use the full case, yet we want the hardware to be optimal. In such cases, use the default clause with an output value of X. So we specify, in this case we say default out is equal to X. This tells DC that okay boss, this is full by design, it will take auto in the inference support, and now we are free to use the don't care bit during optimization. If we use a full case directive, the gate level simulation might not match the RTL. Why? Because let's say there is a case which occurs which you did not specify in your case block, and if the case actually occurs, then it will not match the RTL simulation whenever the case expression evaluates from unspecified input value. So this is a problem. If you use a default case, simulation mismatch can only occur if you specify don't care condition and the case expression. So in the first case, when you use full case and your simulation mismatch occurs, it is difficult to debug. But in the second case, since you set the output value to X, it is easier to debug. So it is always preferable to use a default clause and not use full case. I'll summarize this lecture. This is the last slide. So we saw how to read the RTL, what commands to use. So for reading RTL, I would recommend you analyze library. You can use read file for either netlist or for reading very simple RTL without parameters. So you use analyze, elaborate. Then we saw the example of inference report for register. This is very important to study, to take some time and study the elaboration report that comes out after you read the RTL. We saw how to separate combination and sequential always blocks to make sure that number of registers is minimal. We saw the coding style for FSM. There's one very good example here. You can follow this for your FSM coding. Then we saw very important concept of compiler synthesis directive. We saw a few famous synthesis directives. Again, the recommendation is first code without synthesis directive. Only use synthesis directives when your coding style is not able to solve the problem. Because usage of synthesis directives, since the synthesis directives are ignored by any other tool, any simulation tool, it might cause simulation synthesis mismatch. And simulation synthesis mismatch is not a desirable condition. It is difficult to debug. You have to again review your RTL code and so on. Thank you.